Welcome to Spaceverse, your portal to cosmic adventures. Coarse clouds of hot sand blow in the powerful winds of these two failed stars, a scene that sounds almost alien, yet it unfolds just a few light years from our Sun. Thanks to the James Webb Space Telescope, scientists have now observed this phenomenon in unprecedented detail, effectively producing the most comprehensive weather report ever made for a pair of brown dwarfs. Brown dwarfs are often called failed stars because they occupy a strange middle ground between planets and stars. They are too massive to be considered planets, yet not massive enough to sustain hydrogen fusion, the process that powers stars like our Sun. Instead, brown dwarfs emit faint heat and light, mostly in the infrared spectrum, which makes them ideal targets for JWST's advanced infrared cameras and spectrometers. The two brown dwarfs in question form a binary system known as WISE 1049AB, discovered in 2013 by NASA's Wide Field Infrared Survey Explorer mission. At just 6.5 light-years away, they are among our closest cosmic neighbors, making them a prime subject for detailed observation. JWST's powerful instruments have allowed astronomers to detect dynamic atmospheric changes occurring within these brown dwarfs, including swirling sand clouds made up of silicate particles and extreme temperature variations across their surfaces. These weather patterns resemble massive, planet-sized storms, where the clouds are not made of water vapor like Earth's, but of tiny mineral grains and metals heated to thousands of degrees. The findings suggest that brown dwarfs are far from being static, dim objects. They are dynamic, turbulent worlds with complex atmospheres, possibly similar to those found on giant exoplanets orbiting distant stars. By studying WISE 1049AB, scientists gain a deeper understanding of how atmospheres behave under exotic conditions, knowledge that can also help interpret the climates of massive gas planets beyond our solar system. JWST's observations bridge the gap between stellar physics and planetary science, showing that even failed stars can hold the key to understanding how worlds and weather work across the cosmos. A brown dwarf is a type of celestial object that sits in a cosmic gray area. It's not massive enough to sustain hydrogen fusion, the process that powers true stars, but it's far too big to be considered a planet. Think of it as the missing link between gas giants like Jupiter and small stars called red dwarfs. Brown dwarfs form the way stars do, collapsing from massive clouds of gas and dust under gravity. But because they never ignite into full-blown nuclear fusion, they spend their lives dimly glowing in infrared light, slowly cooling over billions of years. Astronomers have been studying brown dwarfs for decades, but there's always been a limitation. Most past observations were like still photographs, a single snapshot that captured what these objects looked like at one moment in time. What scientists really needed was a movie, a way to watch how their atmospheres change and evolve. That's where the James Webb Space Telescope came in. Unlike any observatory before it, JWST has the ability to watch objects continuously over many hours and detect tiny changes in their brightness and spectra. This allows scientists to see how weather patterns form and shift in real time, even on distant worlds. The team, led by Beth Biller from the University of Edinburgh, focused on WISE 1049AB for a combined 15 hours of continuous observation, 8 hours using JWST's mid-infrared instrument, or MIRI, and 7 hours using its near-infrared spectrometer, or NIRSPEC. What they discovered was nothing short of spectacular. Both brown dwarfs are blanketed by tumultuous, fast-moving clouds likely made of silicate grains, essentially tiny particles of hot sand. These clouds churn through atmospheres with temperatures reaching between 875 and 1026 degrees Celsius, or roughly 1610 to 1880 degrees Fahrenheit. Imagine a storm where, instead of water droplets, molten sand grains are whipped around by hurricane-force winds. The JWST also picked up the spectral fingerprints of carbon monoxide, methane, and water vapor, gases that help paint a clearer picture of the composition and chemistry of these exotic atmospheres. But the most revealing data came from studying how the light from each brown dwarf changed over time, a graph called a light curve. Each brown dwarf's light curve showed dramatic fluctuations in brightness. This variability wasn't random, it hinted at something deeper. The scientists believe the changes are caused by storms and shifting cloud patterns, thick clouds forming, thinning, and breaking apart as the brown dwarfs rotate. When gaps appear between those clouds, we can see into deeper, hotter layers of the atmosphere. because the two brown dwarfs spin so quickly, one completing a full rotation in just 7 hours, and the other in 5, JWST was able to capture multiple rotations during the observation. That gave scientists a kind of time-lapse view of how their weather systems evolve. Even more fascinating were the specific wavelengths of light that showed peaks and dips. JWST detected strong signals that corresponded to carbon monoxide, methane, and silicate grains. These spectral clues revealed something groundbreaking. Each brown dwarf has multiple atmospheric layers, each with its own pressure and temperature. Dr. Biller's team interpreted the data as showing 3 distinct layers: a deep layer, an intermediate layer, and a high-altitude layer. In other words, JWST didn't just see the surface of these brown dwarfs. It peeled back their atmospheric structure, layer by layer. This is the first time scientists have been able to map out the vertical profile of a brown dwarf's atmosphere in such detail. Before JWST, we could only guess at what might be happening in these alien skies. Now we can watch their weather unfold in real time with data that shows how pressure, temperature, and chemical composition change with altitude. It's like going from looking at a shadowy outline to suddenly seeing a fully detailed 3D image. But beyond the immediate discovery, this study opens an entirely new window into exoplanet research. Brown dwarfs are, in many ways, natural laboratories for studying giant exoplanets. They're easier to observe because they don't orbit bright stars that overwhelm their faint glow. Yet they share similar atmospheric properties, clouds, chemistry, and even weather dynamics. By refining techniques on brown dwarfs like WISE 1049ab, scientists can apply the same methods to gas giants orbiting other stars and eventually to potentially habitable exoplanets. As Beth Biller herself said, "Our findings show that we are on the cusp of transforming our understanding of worlds far beyond our own." These insights don't just tell us what's happening on these failed stars. They also help us understand how atmospheres evolve, how cloud systems behave, and how heat and light move through alien skies. Eventually, this kind of research could help detect weather patterns on Earth, like planets orbiting distant suns, places where clouds might not be made of sand, but of water, methane, or even exotic compounds unknown to us. It's astonishing to think that JWST can measure all this detail from an object 6.5 light-years away, about 38 trillion miles. Its ability to sense the faint flicker of infrared light and translate that into a dynamic weather map of a distant world is one of humanity's greatest technological achievements. And this is only the beginning. The researchers emphasize that this study is the first of its kind, but definitely not the last. In future observing cycles, JWST will continue to monitor more brown dwarfs and even young exoplanets, giving us a clearer view of the diversity of weather across the universe. Each observation adds another piece to the cosmic puzzle. How do atmospheres form, change, and behave in environments far more extreme than anything on Earth? Imagine, for a moment, standing on a world where the sky glows dimly red, and clouds of vaporized rock swirl above you, scattering light through a haze of molten glass. Winds roar across the horizon, hurling silicate dust at thousands of kilometers per hour. That's the kind of alien weather JWST is now revealing, storm systems that make our most violent hurricanes look calm by comparison. Through discoveries like these, we are not just learning about brown dwarfs, we are expanding the boundaries of what weather even means. Because on worlds like WISE 1049ab, the forecast isn't just cloudy, it's literally raining sand. As JWST continues its mission, each new discovery brings us closer to understanding not only the atmospheres of brown dwarfs and giant exoplanets, but also the fundamental processes that shape every world in the universe, including our own. From the dim glow of failed stars to the potential blue skies of habitable planets yet to be found, JWST is transforming astronomy from distant observation into detailed exploration, one stormy alien world at a time. In the end, the discovery of sandstorms raging across brown dwarfs like WISE 1049ab reminds us just how diverse and unpredictable our universe truly is. Even in the quiet spaces between stars, entire worlds swirl with motion, heat, and mystery, each one rewriting what we thought we knew about the boundaries between stars and planets. As the James Webb Space Telescope continues to peel back the layers of cosmic weather, who knows what other strange and stormy skies await discovery. Thanks for watching. If you enjoyed exploring the wild weather of failed stars, don't forget to like, share, and subscribe to Spaceverse for more deep space discoveries. And remember, out there, even the calmest light may hide a storm.